Hello, students. Today we are going to learn more about the support force, also known as the normal force. This support force acts perpendicular to the surface. For example, if I have an object like this one sitting on a surface, then the normal force will act perpendicular to the surface. We draw it like this. We label this normal force, and the other force will be gravitational force pointing downward like that, right? Of course, I have to make sure that the sizes are equal in this case. So I'll draw my normal force as this and gravitational force like this, most same size. Support force and gravitational force right there. Okay, so this support force is also called normal force like that. Now we are going to learn the support force in different situations. The first case will be the case whereby the object is at rest, like this case. So let's start object at rest. Object at rest. Okay, sure it's reading nicely. Object at rest. When the object is at rest, we just draw our flat surface like this, and our object will be here. Then we draw the forces starting from the center of mass, the center of the box. The first force will be gravitational force, Fg. I'm going to use mg throughout for gravitational force. That's the mass times g, which we also call the weight of the box. And the normal force will be right here. We call this one, we'll be using the support force, F sub s throughout. I try to draw the forces of equal sizes for a reason. Let's see what Newton's second law will tell us about these two forces, Fs and Fg. According to Newton's second law of motion, the sum of forces in the y direction must be equal to mass times acceleration in the y direction. Here we have two forces that are acting in the y direction, Fs upward and Fg downward. So we are going to say this is actually equal to support force plus minus mg. I'm putting Fs with a positive sign. There's a positive sign here because it's acting upward, and mg has a negative sign because it's acting downward. The result must be mass times acceleration in the y direction. But I realize that the box is not moving, it is at rest, and so the acceleration is 0. Therefore, everything here goes to 0. Then I can say support force is equal to mg. Here, we learn that when the object is at rest, the support force is actually equal to the weight of the box. So support force is equal to the weight of the box. Support force is equal to weight of the box, right? Things will not be like this all the time. This is a special case whereby the object is at rest, and we learn that the support force is actually equal to the weight of the box. Only in this special case whereby the object is at rest or it has acceleration of 0. Now we are going to see different situations whereby the support force will not necessarily be equal to the weight of the box. For example, let's see a case whereby you push the box downward. Imagine push the box downward. And let's talk about the support force in that case. As usual, I'll draw my surface. The surface. I put my box here, and I draw my gravitational force downward. This is my gravitational force. I'll just put mg, and then I'll put the force that I am pushing, small one. This is the pushing force. And then there is also the scale force. which is acting upward is actually normal, remember, so be this one. This will be my my normal force. That's support force. So right now, I would like to learn the relationship between the support force and the weight, which is mg. Just use mg. I'm not using mf sub g anymore, just mg. I'm going to apply Newton's second law of motion again. The sum of all forces in the y direction must be equal to mass times a in the y direction. Here, I'm going to understand that acceleration is also equal to 0 because the object is still at rest. Still at rest, that's the condition. It's not moving. I'm just pressing down with a force P here. If this is 0, then the result here is 0. Then I can rewrite this considering all the variables I have in this problem. I have Fs acting upward, so I'll write it like Fs. There's a plus here, but I don't put it. And then I have minus P, so I'll add force. The pushing force is acting downward, so I'll put minus P here. And then I have mg. Mg is acting downward, be plus minus mg. The result must be 0. If I do that, I see that the support force is actually equal to the pushing force plus mg here. In this case, I can say that the support force is not equal to the weight of the object. Actually, the support force is larger than the weight. Support force is larger than the weight of the object. By definition, we're using weight as mg. So in this case, we see the support force is larger than the weight of the box. Now, let's look at another situation whereby we are pulling the box at an angle. Pulling the box at an angle. That's the other situation, pulling the box at an angle. This situation tells me that I should have my surface as usual, and then I'll have my box here. Then I'll have to consider the fact that there is a small pushing force here. I call it P. There is, of course, gravitational force acting downward, mg, F sub g or mg. And there is also friction that is causing this object to remain at rest. So I'll draw friction force here. This is a force of friction. These are the 3 forces acting, but also I have to remember there has to be some support force. So there is a support force. Support force there. Right? Let me write it somewhere away from the P, somewhere here. There is also the support force. It is very important to recognize all the forces acting on the box. If you forget to include one of the forces, the analysis will not be valid. So here I have exhausted all the forces. I have the weight, mg. I have my frictional force that is keeping the object there at rest. I have the pulling force, P, at an angle, and I have support force here. But I would like, the most important thing I want to learn, what is the relationship between support force and the weight of the box? To do that, I need to break down the force P into X and Y components. I can try to break down P into X and Y components. So first of all, the X component of P will go this direction. Let me use a different color. I'll use a different color for that. Maybe let's take blue. So there is this component. This is the component of P in the X direction. I break down P, so this will be Px, and I can break down P upward like that. That will be P sub Y. So I break down P, that means P can be neglected in our analysis. I have broken down P into the horizontal component and the vertical component. This is what we do with the parallelogram rule. We can break down a vector into perpendicular components, Px and Py. That means now all the forces are acting in the y direction and in the x direction. I can then apply my Newton's second law analysis. The net force in the y direction must be mass times acceleration in the y. And since there's no acceleration in the y direction, then I can say that this is zero, or zero, the whole thing is zero, okay? And then I can actually say, what is the sum of the forces in the y direction? Let's start with Fs. Fs acts upward, so it will have a positive sign, Fs, plus I see Py. Py acts upward, so it will be Py the way it is. Then I see Mg. Mg acts downward, so it will be minus Mg. That will be equal to 0. If I do that, I see that I can now say that the support force is equal to, I see Mg minus Py. So that will be Mg. If I transfer this to the right-hand side, it'll be plus Mg. And if I transfer this to the right-hand side, it'll be minus Py. So in this case, I see that the support force is less than Mg. So support force is less than Mg, or the weight. Support force, I'll use this symbol, less than. This means less than weight of the box, the weight of box. And remember, the weight is Mg. This tells us the support force is less than the weight of the box. Remember the situation here, you're pulling the box at an angle and the box is still at rest. That's the condition, at rest. And that's why we were able to say that the force of friction here balances the component of the pulling force in the x direction. The box is still at rest. You're just pulling at an angle, and we end up with a conclusion that the support force must be less than the weight of the box. That makes sense. That makes sense because we see that the pulling force is helping. This component here is helping with pulling the box upward. All right. Now let's look at the other case whereby we have the elevator case. So we are going to look at the situation, support force in an elevator. Support force. But we're going to look at elevator case. Elevator case. Again, we have our floor, but now this floor is the floor of an elevator. And we have our box here. This box is in the elevator, and the elevator is accelerating upward. Acceleration is upward, is positive acceleration. That means the elevator is accelerating upward. This entails that gravitational pull, Mg, is less than the support force, Fs. And the elevator is accelerating upward, and the box is sitting on the floor of the elevator. For that reason, I can apply my second law as follows. Okay, I'll start by saying that the net force in the y direction must be mass times Ay. Now, the net force in the y direction will be given by Fs, which is acting upward, plus minus Mg, because Mg is acting downward, it will pick a minus sign, equal to mass of the object, the mass of the object here, and then times acceleration in the y direction. We are going to write a y here. Now here we see that we can now find Fs in terms of Mg and Ay. So I'm going to put Fs one side of the equation, transfer minus Mg to the right-hand side. It will be plus. Then there is also plus May. Then the support force will be equal to, I'll take out M M will be taken out, and then open bracket, G plus AY. So I'm trying to rewrite this so that M is out of the equation and G and AY remains inside. Just factorizing, I should say. That's factorization. This tells me that the support force depends on the acceleration. If acceleration is positive, then the support force will be larger than the weight, which makes sense. In this case, when AY is positive, like positive acceleration, it entails that the support force will be larger than the weight. The support force will be larger than the weight because this component, let me show you, this component here will be positive. This will be positive. And if you add it to this one, it will show that the support force will be larger than mg. In other ways, if you are in the elevator, you will feel heavier because of this pulling, upward pulling, you will feel heavier. The support force is larger because you are accelerating upward. This dotted line shows acceleration in the upward direction. As you can see, if the acceleration is negative, if you make this component negative, then the support force will be less than the weight of the object. If our acceleration is negative, then the support force will be less than the weight of the object. If the acceleration in the y direction is 0, then we are going to go back to the first situation whereby Fs will be equal to mg. All right, so I would like you to make sure you understand the effect of the support force, the effect of the acceleration on the support force. What will happen if acceleration in the y direction is positive? What will happen if the acceleration in the y direction is negative? What will happen if the acceleration is 0? That will tell you the relationship between the support force and the weight mg of the object. All right, let's look at our last situation where we are going to talk about the support force. And now we are going to talk about the support force for a case where we have an inclined plane case. So let's look at inclined plane. For an inclined plane, let me use red here. We are assuming that we have an inclined plane. I'm going to make my inclined tilted, inclined like that. And I'm going to put a box here. So the surface, my surface is actually the inclined plane. And then I realize that there is gravitational pull acting on this one, gravitational pull, mg. And there has to be a normal force, of course, normal force here, which we call support force. Now I can have my coordinate as follows. So this is the y direction, and this one will be the x direction. So y, and this is my x direction. That means going this way is positive, down here is positive. Otherwise, everything is negative. All right, I have drawn the gravitational force straight downward. It is vertical. It is going straight, actually parallel to this vertical line here. And the support force is perpendicular to the surface, perpendicular to the surface of the inclined plane right here. Now I have to, let me fix this. That to look nice. This has to look nice. Yeah, like that. Okay, and now I have to realize that these are the forces that are acting on this. And I'm assuming that the surface is frictionless. We assume that there's no friction on the surface, and therefore these are the only forces acting. We have mg and fs. You might wonder, why is it that I have drawn mg longer than fs? The reason will come out clear very soon. First of all, let's use the parallelogram rule to break down mg into a component in the x direction in the y direction. I can use a different marker. So let's use this marker. A component in the x direction will be drawn here. This is the component of mg in the x direction, all the way here. This is the component of mg in the x direction. And then I will label that as mg in the x direction. And then I can also draw a component of mg in the y direction, all the way there. I call that mg and then sub y. I have broken down the force mg into the y component and the x component, like that. That's what we do when we use a parallelogram rule. Again, we can see that this is perpendicular there, perpendicular to the inclined plane surface. And these are components of mg. That means I can say that I no longer have to care about that because it has been represented by the component in the x direction and the component in the y direction. It has been represented by those two forces. As you can see here, we can apply our Newton's second law in the y direction. It must be equal to mass times acceleration in the y direction. If I do that, I realize that there is no acceleration in the y direction because the object is accelerating downward. There's no friction. Since there's no acceleration, this goes to 0. And therefore, what I'm saying here is that the net force in the y direction is 0. And I realize that I have two forces that are acting in the y direction. I have Fs, and then I have another force, which is a mg sub y, but it's acting down opposite to the positive y axis, mg sub y, like there. The answer must be 0. The result of this analysis is that the support force is actually equal to mg sub y. This you can tell already here that the Fs must be equal in magnitude to mg sub y. As you can see here, already you can tell that the support force is actually less than the weight of the object. The support force is less because we know that mg sub y is actually less than mg. See, mg is here and it's actually longer, and mgy is shorter. Mgy is less than mg, and therefore we can conclude to say that Fs is less than mg. The conclusion here is that when a box is sitting on an inclined plane, the support force, which is this one, is less than the weight of the object. You can tell what can happen if you continue elevating the inclined plane, make it steeper and steeper. You can tell that the normal force or the support force will be diminishing, will be getting smaller and smaller until it is 0. It will be 0 when the inclined plane right here, when the inclined plane is vertical, there will not be any more of the support force or the normal force, right? This marks the end of our discussions. We have seen the normal force in different situations. We started by looking at the case of an object at rest. We realized that when the object is at rest, the support force is equal to the weight of the box. And we looked at another case, and the other case was the case whereby we push the box downward, maybe using your hand, try to press the box downward, but still the box is at rest. Our analysis has indicated that the support force turns out to be larger than the weight because we're adding the P there. The support force is larger than the weight, right? Support force is larger than the weight of the box. Our analysis indicates that we are going to have a larger support force. And then we had another situation, and this situation was whereby we are pulling the box at an angle, but the box is still at rest. Our analysis indicates that the support force is less than the weight of the box, because the pulling force helps you somehow. So in that case, the support force is less than the weight of the box. And finally, or not finally yet, but we looked at the elevator case. For the elevator case, we saw that the support force can be actually more than the weight, less than the weight, or equal to the weight, depending on the acceleration. And if the acceleration is positive, like in the case we analyzed here, if the acceleration is positive, like accelerating upward, the support force is larger than the weight of the box. If the acceleration is negative, the support force is less than mg. If the acceleration is 0, then the support force is equal to the weight of the box, just like in case 1. And finally, we have looked at the inclined plane case. For the inclined plane case, we saw that the support force is less than the weight of the box. And the support force becomes 0 when the inclined plane is vertical. Anyway, that's it for now. If you have any questions, please let me know. I'll go for now. Bye-bye.